Hello, everyone, and welcome back to your own channel, Capsulated Breakthrough. We are back again, as promised, 1 week later, and today we've come with another new topic and another new subject as complete. Yes, as you all know, my name is Syed Irfan. I'm pursuing Electronics and Communication in Sri Venkateshwara College of Engineering. Yes, and today we are back with a new topic that is in control systems, where we'll be talking about the fundamentals of control system, covering understanding translational mechanical system and rotational mechanical system. And at the end, we will be solving a question which is related to the block diagram reduction. Okay, so you all know that we will not waste a lot of time in introduction because we have a bandwidth of time in which we have to make this video. Right. So without wasting much time, let's start. So we will be discussing about the fundamentals of control system today, starting with the introduction of control system, that what is control system and how control system works, and what are the translation and the mechanical rotational systems. So the first one is overview of control system. So what do we mean by control system? Before we start anything, control system is a complete subject you'll be studying when you come to your fourth semester in electronics and communication. That is really interesting problematic subject where you will find different types of problems and you'll be happy to solve those problems if you get good teachers like I have one. Okay, yeah, so enhancing system performance through control loops. First, what is the essential role of control system in engineering? We'll just take a brief outing of what control system is, and then we'll go to the main topic, right? So control system plays a vital role in managing and regulating various engineering processes to ensure efficiency and accuracy. So, to ensure the accuracy, control system plays a very vital major role optimizing the manufacturing process. Okay, by using control system, manufacturing operations can be optimized, resulting in improved quality and productivity. So the control system is directly proportional to the productivity and improved quality of the items. Right. Moving on next. Okay, now we've jumped on to the main part where we'll be taking a lot of time and discussing what these things are and how does this work. The first thing to discuss in today's topic video is translational mechanical system. This come in the under the control system only. So what is translational mechanical system? Exploring the linear motion in control system. So basically translational mechanical system is a synonym for the linear motion. Linear motion description is translational mechanical system involves linear motion where components such as mass, spring, and damper play a crucial role. See, we have to understand that in linear motion, in linear mechanical system, you see the mass, the spring constant decay, and the damper which play a very crucial role. Some of the key components are the translational mechanical system are mass, spring, damper, each contributing unequally in system dynamics. So for any system control, linear motion control, it is very important to know the mass, very important to know the spring constant of that particular material, and the damper to which you can find the actual translational motion mechanical system of that particular object. We'll be covering I will be telling the formulas at the end. We will be covering solving some questions on this, right? So without wasting much time, let's move on to the next slide, which is, yes, this is the diagram of the translational mechanical system, not exact diagram which you see in the questions. This is just a brief showcase on how what are the important things you need, what are the important units you need when you solve a question on the translational mechanical system. Right. The first most important thing you would need is the mass. M represents the mass of the object in the system, and then damper, which is B, shows the damping coefficient, indicating the resistance of the motion. Damper shows the resistance of the motion, which is denoted by B. Then the displacement X. This makes a very crucial. Represents the distance of the mass has moved from its equilibrium position. Then the spring constant K, as we all know, we discussed about this in the previous slide too. And then the most important thing which is needed for finding the answer for your questions of the translational mechanical system is the force. Because if you have force, it is very easy to find the translational mechanical system, right? Okay, moving on to the next slide. So what is the rotational mechanical system? So now we've understood what is translational mechanical system. which is a linear movement of the mechanical system. Oh, I'm sorry. It is the linear movement of the mechanical system. Now we've got it. We've got the formula, not the formula actually, but we've got all the units. We've understood how it works. Now let's try and understand how does a rotational mechanical system works. Understanding that, the first thing is the rotational motion, then the key components and the equations of the motion. Right. Okay. By the diagram just depicts the bar graph that is nothing related to the actual rotational mechanical system diagram. There is a block diagram which I'll be portraying in the last slides. Right. So the diagram shows us that the moment of inertia J is very important in this. Then we'll have the same damping constant, the damper constant B, and then the angular displacement theta. Theta plays a very vital role. We don't have usually see displacement of angle in the translational motion, but yeah, there is a displacement angular motion at the rotational motion, that is theta. Then the same we see the spring constant k. Then yeah, whenever there's a rotational motion happening, guys, remember there will be an application of torque. Torque is the force causing rotation measured in the newtons per meter square, right? So the last system equilibrium, balanced state where the sum of the torques equals zero, indicating no net external torque is applied on it, right? So the most important thing is we need the moment of inertia J, damping constant, angular displacement theta, translational constant, spring constant K, and then the torque and equilibrium state. These are the most important units, notations, which are very important for finding out answer solutions for any questions of your rotational mechanical system. Right. On to the next slide. So what all can you, not understanding the basics of block diagrams and reduction in the control system, the graphical representation, signal flow depiction, system component relationships, complexity and simplicity. These are the major parts which will be breaking down a control system question into and answering those. Right. So, example of a block diagram reduction. How would you reduce? Identify the block in a series. So now we've come to a block diagram. There are, if you've come from an VTU, there are many major questions on block diagram which you will have to solve. Right. So block diagram reduction is very important. I've explained step by step what you have to do in reducing a block diagram. So for the first thing is you have to identify the block in the series, which is the block. Recognize the combined consecutive blocks to simplify the diagram. The second is eliminate the feedback loops. You have to take the feedback loop, right? Excuse me. Yeah. So you have to eliminate the feedback loop, remove the feedback loops in a streamline and block the diagram, right? Enhance the clarity and understanding of that feedback loop and achieve a clearer representation for a better comprehensive system. Then combine the blocks in the parallel. See, if the blocks you can find blocks either in series or in parallel. If the blocks are in series, just multiplied. Like if G1 and G2 are the two blocks which are included in series, then you can just take it G1 into G2. But if the blocks are in parallel, like G1 and G2, then the blocks will end up as the sum of G1 plus G2. I will be explaining all these again when I solve a question. So kindly be patient and watch the video till the last, right? So the next, reduce the complexity step by step. It's very important that first you find the block, first you minimize the block, see if it is in series or in parallel. Find that, then go to the feedback loop, find the feedback loop, eliminate the eliminate the cross points and at the feedback loops, then ensure the proper block connections, maintain correct connections to preserve the integrity of the system representation. Right. So, what are the application of these mechanical systems? Where do we actually apply the mechanical system? Either it's translational mechanical system or it is the rotational mechanical system, whatever. But where do we apply them? Right. First is the automotive industry, suspensions. We happen to see these in the automotive industry a lot, hell lot to be honest, in the automatic suspension systems. Then comes the robotic arms. Rotational systems play a vital role in the design and control of a robotic arm. Then the efficient control system design. We see this in the control systems, laboratories, or the online applications of control system. These are very important in those aspects also, right? So we see these in these many aspects. Yeah, so these are the things, ladies and gentlemen. We see them in where did it go? Yeah. So these are the major things where we see the system, mechanical systems, and the rotational system. Do not leave the video just because you can see me is not. It's not mean that the video is end. We have come to an end. Oh, till now, if you're there, thanks for watching the video. Keep watching more because we will be covering a question right after I escape from here. I'll be coming back with another set of the atmosphere paper blank where I'll be solving one of the very important question which where you can clear the concepts of block diagram, feedback loops and everything. So stay tuned until then. I'll be back.